My name is Ben Oberkfell. I'm a Android developer at the New York Times, and I'm here to talk about some of the new changes in biometrics in Android P, and also some cool stuff you can do for helping your users make more high-risk transactions on their device. So I'll open this up with the usual sales pitch. We're hiring at the Times, so come out and check out our table in the sponsor hall. If nothing else, if you're playing sticker Pokemon and want to catch them all, we've got a whole stack on the table there for you. So we're going to go over some of the new and new-to-you features in Android 9. Some of these include new support for new biometrics. There's a new prompt for getting biometric authentication from your user. And there's also a new feature called protected confirmation that lets you provide the user an opportunity to authorize sort of high-risk, high-stakes transactions. And we'll talk about what that means in a few. And there's also a feature that came out in Android 8, so it's maybe new-ish, called key attestation, and that helps you improve how you use private and public keys in your app. And protected confirmation kind of ties right into that, so we'll be going over that too. So Android 9 introduces some new concepts in biometrics. It de-emphasizes fingerprint and kind of generalizes the concept of biometric auth. So the CDD kind of finally acknowledges the existence and the inclusion of other biometric modalities. Things like, for instance, maybe iris scanner, or I know another platform out there has a facial ID recognition system, and in addition to fingerprint. And it also sets out a set of strength metrics to make this kind of an apples-to-apples comparison to fingerprint. So you can kind of make a decision on what these mean when your users use them in your app. So I don't know if you've read through the Android CDD. It's good reading when you've read through all the way to the end of the internet and you still can't fall asleep. But it is good to know if you're a developer what's in there. One of the things it mentions here is how we classify and look at other biometric sensors beyond fingerprint. So it sets out some rules about how good these sensors can be in terms of whether they accept bad inputs or how they respond to people trying to fool them. So one of these metrics it puts out is called a false acceptance rate. And this is the chance of accepting an outright wrong input. So if I grab one of your phones off from you and put my finger on it, this is the possibility that it's going to accept my finger incorrectly. So the CDD has required that these implementations have a false acceptance rate less than 0.002%. So restated, that's 2 in 100,000. So they've also kind of laid out these rules for other biometrics too, in terms of spoofing. So this is the likelihood of accepting a known good sample, kind of like a replay attack. So one of these is if you use a fingerprint mold and try and put that on the scanner. I got an image of a set of gummy bears here because there was a story in the news, about 2002, of someone using gummy bears to lift a print and then put them on a fingerprint reader, and it accepted it. So obviously things have gotten better since then. Other ways you might try and do a replay attack in a biometric reader might be a high-res facial picture, a mask. If you're doing voice print, maybe you might replay a tape of someone's voice. Or if you're trying to fool an iris scanner, maybe an iris image on a contact lens. So it also kind of codifies a definition of an imposter acceptance rate. So this is a likelihood of trying to mimic a known good sample and having it accepted. So that's trying to look like the device owner. Maybe you use some makeup or a hairdo, or maybe you're trying to fake the tone of voice or an accent to sound like the device owner if you're trying to fool a voice print authentication system. And so with all these kind of failure modes that they've defined and how likely it can be to accept these, they've defined these classifications of strong and weak biometrics. So strong ones are those that meet these 7% thresholds, where it won't accept one of these bad inputs more than 7% of the time. Weak ones are those that fail that 7% threshold. So weak ones might be allowed to unlock a device, but they can't be used to unlock keys in the key store that have the authentication required flag set. Now also in this new biometric prompt API that came out in Android 9, which we're going to talk about, this API isn't going to expose these other biometric methods. So one thing we've now got in Android 9 is this new set of layers for talking to the biometric services. So previously in Android 8 and below, when you want to do, say, a fingerprint authentication, you're going to go and talk to the Fingerprint Manager class or the Fingerprint Manager Compact class. So now in Android 9, that's been deprecated, and you don't talk directly to the biometric service class. You're going to talk to a biometric prompt or a compat library that does that work for you. And the prompt library is going to be what's talking to these individual services for each biometric modality that's supported within Android. Now, Android 9 out of the box and what's in AOSP simply delegates to the Fingerprint Manager. And that's kind of stated in the documentation that they don't overtly support anything other than fingerprint. Now, however, the documentation for OEMs and system builders and integrators has some information on how, if you're a device manufacturer, how you would go and edit and modify the biometric prompt class to go and provide hooks for your own implementation of a biometric for your device. So what you get with this biometric prompt is a one-stop shop for asking the user to authenticate for whatever their device offers you. And one nice thing about this is that I kind of looked along my Android device, and every app seems to have a different way of prompting the user for biometrics. And I've kind of obscured the names here because it doesn't really matter. But one common aspect that they said in the Google Docs for these was to use the material design fingerprint icon, and that's about the one common thing that everyone has done. And otherwise, everyone's kind of taken their own tack on it. So what we get now is something that's a lot more cohesive, and you're going to find this screen all over your phone, starting with Android 9. So we have a video here. We'll go ahead and let's see, it's a video playing on that. There we go. So the prompt gives you the ability to go and put some helpful information for the user and has some really helpful informations. So here's how to use it. It's a lot simpler than before because now you don't have to define your own UI for a biometric prompt. You just go ahead and put what information you want to have in the prompt with the title, subtitle, description that's going to be presented to the user. You might have a cancellation hook for if they want to back out. Since you're going to use this to unlock an encryption key for some purpose, be it signing or encryption or decryption, you go ahead and create a signature, load the key into it, and apply it to the crypto object, which is sort of a wrapper that the biometric prompt provides for wrapping that encryption primitive. And finally, you're just going to say authenticate. And that'll throw up the dialog. Now, one thing that's kind of helpful here, too, that they've added is that there's a parameter here for executors in launching the prompt. So if you want to control what thread these callbacks land on, now you can do that. And then Android 9 also added this helper method in context called getMainExecutor that lets you get an executor right through your main thread. You also get a callback that tells you what happens when different outcomes come out of the authentication. So, for instance, if the capture was good, but outright wrong, you might get the authentication failed callback. If there was an error like too many tries, or the sensor has already been locked out because you used too many tries somewhere else, and it's a hard error, that have a callback to this one here. And you get an error code and also a error message that's going to be provided by the platform. So this way you don't have to worry about disambiguating yourself what the error message means. It's been given to you by the platform. It's been localized and all that good stuff for you. You just have to go and deal with it. There's also a help message. For instance, maybe the sensor was dirty. You need to clean your lens or your fingerprint sensor. Maybe you've moved your finger too fast. These are help messages that get passed across like that. These aren't hard errors. There's also a success callback. So we succeeded at reading the fingerprint or whatever biometric. So we get passed a result that has a reference back to that crypto object that we had passed in the first place. So we can grab that crypto object out and grab the encryption primitive that it wrapped, be it a signature or a cipher for encryption or decryption, and go ahead and use it. And at that point, the key that we had set as authentication required is available for use. So there's also a support library version, but it unfortunately isn't published right now as of the time of me giving the speech today. So you can find it, though, in androidx.biometric. And since Android X has been open sourced and that development is happening out in the open, you can go to the AOSP Android X repository and take a look in there and see what the API is going to start looking like. And what it does is it's going to present either the biometric dialog on its own, if you're on an Android P device, and all the good stuff that comes along with that, or it's going to present its own standardized fingerprint dialog for older devices. So one way or another, you don't have to worry about presenting your own custom UI for requesting a biometric authentication. So along with this, there's some ways that we can maybe improve the way that we do trust with these biometric authentications. So to kind of cover this, I want to go over what the sort of central theory of how a biometric login to a remote service might work, and where we can go and kind of spruce up some of the trust. So when you go and enroll a new device for biometric auth, you're going to go ahead and create a private key and a key pair for signing something. And we're going to set this flag here, user authentication required. And what happens is this property ensures that the key can't be used unless we have authenticated first. So we're going to have a key in the key store that just is locked down unless someone has successfully gone through the biometric flow. So the idea here is that if I've been able to sign something with this key, I've proof that I've gone through the biometric flow. So maybe to do the client-server flow to enroll a user, you'll go and log in with the username and password like you do before, and you'll trade that for a session token. And on the device side, you'll generate that key pair using that code snippet I showed you. And so that's going to have a public key that you're going to send across. And maybe you'll send a device identifier as well. And this is kind of handy because maybe your user will you'll want to have a UI for revoking the authorization on that one device later on. So you'll go ahead and store that key with the user's data on your back end, however you do it. And you'll give back a device token. So now this token is what your device is going to use going forward to log in without username and password and use the biometric instead. And so let's talk about how that works. You're going to go and present the biometric dialog and sign that device token that you got. And you'll probably also want to include a nonce, which is some piece of data to prevent a replay attack. Now, one really easy, quick and dirty way to do this is to put a timestamp as a nonce. And then when you go to validate it on your back end, what you'll do is you'll make sure that the timestamp fits between some acceptable window that you've set. Maybe it's good for 10 seconds, long enough for a network round trip to happen. You definitely don't want it to be where I capture this session here and then play it back an hour or a week later and have you get let in. So you tape that whole shebang and sign it, and this makes sure that you can't change any of these values without breaking the signature. And the back end is going ahead and verify that signature and the nonce for validity. And if the signature is good, then you go ahead and send back a session token. And then the user can use that token to do whatever transactions in your app, just as they had done if they had traded it for a login and password. So these methods kind of rely upon some trust that the private side of the user's key is securely stored in the trusted world, in the trusted execution environment on the device. So this is a separate processor or a separate portion of the processor running a separate kernel. There's actually a operating system called Trusty that runs. It's part of AOSP that governs the trusted side of the world. And so if your device is rooted or the kernel is compromised, whatever happens in the trusted world is not. So the rules in the CDD, we know that biometric BAT keys are handled by trusted hardware. That's one of the criteria in the CDD, that if you have a fingerprint reader or some biometric hardware, that it deals with keys in the trusted world. However, we want to make sure of a couple things. We want to make sure that that key was securely generated in the trusted world. And we want to make sure that the authentication required flag was set, because we want to make sure that the assumptions we made about that key, that it's only usable if you authenticated, if that assumption breaks, then we don't have a secure system. Or is that key generated by a rando who's used OpenSSL to make a key in the command line, and they're using curl to post it? So how do we know where the key has come from? So what we want is proof of characteristics of the enrolled key. We want to know that it was created in the trusted world. We want to know that that flag was set. And maybe also we want to know that the package name and the signing fingerprint of apps authorized to use that key match what were our own app. And the idea here is, what if I created an app that has your package name but wasn't signed by your signing key, and use that to generate a key on the trusted side, and I'm using that? That's one thing we also want to check for. So what if we also want some secondary characteristics of the device? So maybe verified boot state, like if the bootloader is locked or unlocked. Maybe we want the OS version. Maybe we want the patch level, what monthly patch level you're on. And maybe we want these 4 metrics server side for what our devices are running and how secure our customers are. So how do we find this stuff out? Well, what's really handy is that the certificate associated with the key has an extension block that has all these key generation parameters, and also characteristics about where that key lives, whether it's in the secure world or it was done in software. And up until 8.0, this had been done in software, but software implementations can be compromised, and if you have a device that's rooted, you really can't trust whether it was generated correctly, or if it's been modified somewhere between the device and you. However, the CDD specifies that starting with Android 8, you have to be able to do this in trusted hardware. Now, the question is, how do you pull this off where there are so many different vendors? I don't want to have to worry about a Samsung version of a root key from Samsung or from LG and managing what the device generated for me. So Google has come up with a solution here for what they call key attestation. And they've got a root certificate on their own that's used for key attestation. And this is going to be the final root. Now, when an OEM generates a device or builds a device, at the factory, they generate a key It's like an intermediate signing key. And that key gets burned into the trusted execution environment of every Android phone they ship. And the certificate for that key is signed by Google using the key for the root certificate. So you know that the key that they burn in the device is trusted by Google. So now when you generate a key on the device will sign that certificate with the intermediate key that was burned into it. So now you have a chain of trust from what happened on the device in your pocket to trusting that Google is vouching for the validity of this data by the transitive property of that intermediate key. So one thing that's kind of useful here is that the certificates have a revocation list URL inside it. So when you go ahead and validate these, you can check to see if the intermediate key has been revoked. Maybe for whatever reason that factory key was compromised. And in that case, unfortunately, it pretty much burns the ability to do this on that device going forward because it's burned in the factory. So at that point, once the device has been, its key has been, and its certificate's been revoked, it still is trustworthy as that which does software authentication, but you don't get the sort of assurance you get from the full hardware chain of trust. And one thing they've also done is there's a minimum number of devices that can have a given intermediate key because they don't want you to be able to identify an individual device based upon the certificate for that intermediate key. So I believe it's 10,000 devices is the minimum number of devices that can share one of these intermediate keys. So something getting revoked is going to affect potentially a large swath of devices. Even still, it should be treated as the CDD specifically states that you should not treat a revoked intermediate key as a negative sign, just as a neutral sign, no worse than if you had a software attestation. But you don't get the true strength of Google having vouched for that key anymore. So how do we do this? So we'll create a key with authentication required, just like we did before in that code block we set up to do a fingerprint auth. And we'll go ahead and validate the chain of signatures, and we'll confirm that the root cert is the trusted Google root. And we're also going to go and look into the certificate and make sure that the key has that flag set for authentication required and that was created in the trusted world. And these are values we can check for in the certificate. So on our device, we'll go ahead and get the certificate chain from the key store. And then we'll go ahead and encode these to base 64, and we can send these to our backend. Now, one other important thing is that if you've proven the key was created with the purposes that you want, you also want to prove that the key was created by your command. So you get an opportunity to use a challenge string when you create the key. So your backend might create a challenge string and deliver that to the client before you create the key. Client goes ahead and creates the key with a challenge baked into it. And then when you do this, you send up the certificates, the backend validates that the challenge was there. So when we generate a key, in addition to setting authentication required, we can set this attestation challenge. So you probably want to use something bigger than hello world for your challenge, probably some large amount of random digits. I believe you get 16 bytes you can use max. But this will be something that comes from your back end that then you can go and use to validate later. So let's look at maybe the enrollment flow for a biometric auth now that we can do this attestation. So we'll send up our username and password, trade that for a session token just as we had before. Then we'll send a device identifier up, and our backend will store that ID and generate a challenge. and map those two together so that we can keep track of this flow. Send back the challenge to the user, and on our device we generate a key pair that has that challenge baked into it. So we send up the public key and the certificate chain to the back end for validation, and we go ahead and validate that the key looks good, certificate has the proper chain of trust, and that the challenge is baked into it. And finally, if all that checks out, then we get a device token that says you can use that signing key for authentication going forward. So I've mentioned all this, but how exactly do we validate the certificate? So this is a little bit hairy of a process, unfortunately, because certificates are 20-something-year-old tech, and so much of this stuff is maybe some arcane encoding. So you need to use an ASN.1 parser to pick out the extension data that Android has dropped in the certificate and then read it out. So there's a couple different opportunities here for you, depending on what library or what language you're using. Java, you can use the Bouncy Castle library to go and pick apart cert for ASN and using ASN1 encoding. In JavaScript, there's ASN1.js. Python has its own ASN1 crypto, and there's a good one for Go as well. So there's example code that Google has for Android-specific implementation, and they use Bouncy Castle. And there's a key attestation example in the Google samples GitHub. And this is really what I would look at when you go to implement this for what keys to look for and what to pull out, because they've documented the whole process of parsing the cert and mapping back the flags that are in the AS1 schema that you're going to use, and even mapping those back to where in AOSP these flags get defined. So you can look at how these appear when you parse the cert versus where these get set on the user's device. And there's also a schema that you can review on the Android developer site. We'll look at a little snippet of it here. But you can get information here like whether the certificate was enforced in software or trusted execution environment. You can go and dig out your attestation challenge like we saw before. The attestation security level is whether this attestation happened in software or in hardware. So that's one thing you want to check. And then there's a whole set here of other data that describe the certificate you've created. And so authorization list defines whether we've signed that key whether we've created that key for signing or encryption. You can go and look at the algorithm, the key size, so that you can verify that the strength of the key is what you want. And then you can look for the type of authentication that's acceptable to unlock this key. You can look at the application IDs that are acceptable for using this key. And you can look at when the key was created. So kind of putting all this stuff together, let's take a look at a new thing that's appeared in Android P called protected confirmation. And what this does is they've recognized that we do more and more things with our mobile devices. Some of them are maybe higher risk transactions than we had in the past. Maybe you have, a great example they brought up at I.O. was an insulin pump. So maybe you want to control your insulin pump using Bluetooth. But what you don't want to have happen is somebody rooting your phone and fooling your insulin pump software into telling you that you're going to inject 5 units, but actually having to inject 500 units and kill you. Or you don't want somebody to compromise their phone and change the values that you're going to confirm a bank transaction. Maybe you're going to send me $100, I say, but I've modified your phone to say that you're going to send me $1 million. So what protected confirmation gives you is an API for getting a really high level of confidence that the user actually saw the exact details on the prompt, even if the device was rooted. And so this is available on supported devices that ship with Android 9. Unfortunately, there aren't any devices in the fleet that actually support this right now. But the way this works is that the trusted execution environment takes control and presents a prompt to validate that transaction. So you're going to go ahead and ask Android, I want to prompt the user to transfer 4,200 euro. And then it's going to hand that off to the trusted world, display that prompt, and then if the user accepts or cancels, you get a callback at the end to decide what to do. Now, if they accept it, you're going to sign that data and send it back to your server for validation. Now, the way to do this, though, is you want to make sure that the key that you generated can only be used to sign confirmed data that's gone through that flow. Otherwise, you can't trust that it was actually signed through this protected, trusted method. So one thing you can do when you generate the key is we set this user confirmation required flag as a key generator parameter. So we're going to use key attestation to confirm that the challenge jives with what we want, and we're also going to look for this flag. Now what happens here is that once you've set this flag, this key can only be used to sign data that has gone through the confirmation flow. You can't use it to sign anything else, it'll error out. So having used this key implies that the data that went through it had been confirmed. So you'd issue the prompt. You probably, in this case, want to get a nonce from your backend or your service and use that as a replay protection token. You're going to go ahead and set the prompt text. This is going to be what's displayed on the screen. Send $100 to Ben. You also have a set of extra data. That's a way that you can validate in your own code the transaction you're doing. So we're just going to go ahead and take that same prompt and add the nonce, and we'll use that for making sure that we're not replaying a transaction. And since then we're going to go ahead and build. And this dialog uses the same sort of paradigm we saw in the biometric prompt, where it takes an executor so you can decide what thread the callback is going to land on. So now we'll go ahead and handle that result once the user accepts the prompt. So you would get this onConfirmed callback with the data that they saw. And then you can go ahead and sign that data and send it to the back end. And again, the only thing that you can use that confirmation required key for is data that came through this callback. So the data that comes back to this callback is in the format called CBOR, which is the concise binary object representation. It's a data structure that has a couple key value pairs. One of them is going to be that prompt text, and that's the data that you displayed on the screen. The other is going to be the extra data that you encoded. And so this is where you're going to go and make sure that the prompt matches what you want, and also that the extra data validates your nonce check to prevent replay. So you sign this CBOR data, you send that to your service, and you validate it. And it's important to validate the prompt text because that is the only thing that you really can be sure was displayed to the user. So if that data validates, as does the signature, what you know is that the data was signed using a key that had that confirmation flag because you validated that with key attestation. You knew through the rules that we play with that if it was signed by that key, the data went through the confirmation flow, or else it would not have been accepted for signing with that key. And since you also have checked the nonce, you know this wasn't a replay, and this was a new and unique request. So at that point, then you can go ahead and execute the money transfer or whatever it is that you want it to confirm. So just going to wrap up a few of the things we went over here and some good resources for looking at the stuff in the documentation and Java docs. So there's the biometric prompt in the Android Java doc, and this explains a lot of the error codes that you might see for why things went wrong. That would be passed into the on error and on help messages. You can also check out the Android X source repo for what the compat lib looks like. And it's actually really cool to check out the Android X source anyway for what's going on in the support lib. There's also a training doc on the key attestation, and that includes the full schema for how to parse out that ASN1 structure. And then there's also some resources on protected confirmation on the Android dev site training page. Some other resources I've got. 2016, we had the Android Fingerprint Authentication, where I did a deep dive into specifically how to do fingerprint auth across an Android device. At OrDev, we talked about how to do data at rest encryption using fingerprint. So we had an example that we explored of a diary for the user that you can unlock with your fingerprint. And we also spoke of the Don Felker and Kaushik Gopal on Fragmented back in 2017 in February. And these slides are up on SpeakerDeck at this address here. And with that, thank you very much.